Close your eyes and listen to the rhythmic scrape of several tons of limestone sliding over wet, silken Nile silt. In the shadow of the Great Pyramid, there are no grand speeches, only the hypnotic pulse of wooden sledges and the steady tension of papyrus ropes. Let the methodical weight of ancient logistics carry you into a deep, dreamless sleep tonight. Welcome back, traveler, to Boring History, a quiet corner of the world where we leave behind the noise of today and gently wander into the stillness of the past. Here, the fires of history burn low and steady, casting long shadows over forgotten stories. We are not here for kings and conquests, but for the quiet, strange, and sometimes unsettling moments that time nearly buried. Before you get comfy, go ahead and like the video and subscribe, only if you're actually enjoying it. Tell me in the comments where you're watching from and what time it is for you. I'm always curious to see the mix of places and time zones hanging out here together. Segment 1. The Weight of Ambition. The year is 2560 BCE, and the sun rises over the Giza Plateau, the way it always has, indifferent, blazing, absolute. The desert floor is pale and cracked. The Nile, a green ribbon to the east, reflects the early light like hammered copper. In the distance, the low mud-brick buildings of Memphis, one of the world's first great cities, are already beginning to hum with the business of empire. Donkeys bray, bakers slide flatbread into clay ovens, scribes unroll fresh papyrus and dip sharpened reed pens into black ink made from soot and gum. Somewhere in the palace complex, in a room cooled by thick stone walls and reed screens, a pharaoh is already awake, already thinking about his mountain. His name is Khufu, Khufu in its full form, meaning that God Kun protects me. He is the second pharaoh of the 4th dynasty, son of Sneferu, who himself built not one but 3 major pyramids during his reign, learning from each mistake, refining each technique, leaving his son an inheritance not just of wealth and power but of hard-won architectural knowledge. Khufu inherited a civilization that already knew how to build pyramids. What he intended to build, however, would dwarf everything that came before it. Not incrementally, not modestly, enormously, defiantly, permanently. The numbers, even stripped of all romance, are staggering enough to stop the breath. The Great Pyramid of Giza, known to the ancient Egyptians as Akhet Khufu. The horizon of Khufu would rise to a height of approximately 481 feet at its completion, a figure that made it the tallest man-made structure on Earth for nearly 4,000 years. It would not be surpassed until the construction of the Lincoln Cathedral in England, around 1311 CE, 4,000 years. Let that sit for a moment. The span of time between Khufu's pyramid and the building that finally exceeded it is longer than the entire span of recorded Western history from ancient Rome to today. The pyramid was not a remarkable achievement for its era. It was a remarkable achievement for all eras. Its base covers approximately 13 acres, an area large enough to contain the footprints of St. Peter's Basilica in Rome, the Florence Cathedral, Westminster Abbey, and St. Paul's Cathedral in London simultaneously, with room left over. The 4 sides, each running roughly 756 feet in length, were aligned to the cardinal directions with an accuracy that astonishes modern surveyors equipped with satellite technology. The variation between the longest and shortest sides of the base is less than 8 inches across a combined perimeter of more than half a mile. The base itself is leveled to within 2 centimeters across its entire surface. In an age without lasers, without levels beyond simple water channels, without any instrument more sophisticated than a plumb bob and a stretched cord, this precision was not an accident. It was the product of intellectual systems so refined, so tested, and so carefully implemented that they produced results indistinguishable, at human scale, from perfection. Inside this mountain of engineered stone, the architects placed a system of chambers and passages that still challenges modern engineers to fully explain. The king's chamber, buried deep within the pyramid's heart, is lined entirely with massive red granite blocks, each one transported from Aswan, nearly 500 miles to the south. Above the king's chamber roof are 5 stress-relieving chambers, an engineering solution to the problem of preventing the immense weight of stone above from crushing the room below. The builders understood compressive force well enough to solve it, using a system of corbelled granite slabs that distributes the load outward rather than allowing it to crush straight down. They had no formal physics. They had something arguably more valuable: generational experience, empirical observation, and an instinct for stone developed over lifetimes spent working with nothing else. To build all of this required approximately 2.3 million individual stone blocks. This figure, often cited, rarely truly lands until you begin to think through what it actually means in human terms. If you were to take every one of those blocks and lay them end to end, they would stretch roughly 5,000 miles, approximately the distance from Cairo to New York City. The average block weighs around 2.5 to 3 tons, the weight of a modern pickup truck loaded beyond its rated capacity. The largest blocks in the pyramid, the granite ceiling beams of the king's chamber, weigh up to 80 tons each. Moving an 80-ton block of granite without powered machinery is not a problem with an obvious solution. It is, for most people who first encounter it, a problem that seems to have no solution at all. And yet there they are, 500 miles from their quarry, placed with care, holding the ceiling of a room that has not shifted or cracked in 4.5 millennia. Khufu did not dream this pyramid into existence alone. Behind him stood an apparatus of state, the full administrative machinery of the Old Kingdom Egyptian government, one of the most sophisticated bureaucratic systems the ancient world had yet produced. Tax records, census data, grain inventories, labor rosters, tool tallies, boat manifests, medical logs. The pyramid was not just a construction project. It was a state enterprise on a scale that required every branch of Egyptian governance to be pointed at a single purpose for the better part of 2 decades. Egypt's farmers, miners, sailors, carpenters, coppers, smelters, bakers, brewers, physicians, and scribes were all, in some direct or indirect way, participants in the construction of Khufu's monument. At the apex of this apparatus stood Hammunu, Khufu's vizier, and likely his master architect. Hammunu was Khufu's nephew, a man of royal blood who combined political authority with technical mastery, a pairing that was almost certainly necessary for a project of this scope and ambition. He is depicted in a famous seated limestone statue, now held in the Rama under Pelaseus Museum in Hildesheim, Germany, as a heavy, confident man, his face wearing the expression of someone accustomed to solving large problems. His title was overseer of all construction projects of the king. The pyramid was not merely his greatest work. It was, in a very real sense, his entire career distilled into stone. What Hammunu faced when he unrolled the plans for the Great Pyramid was not primarily an architectural challenge, though the architecture was certainly complex enough. The deeper challenge was logistical. Given unlimited time, any sufficiently large workforce can stack stones into a pile. But the pyramid was not a pile. It was a precision instrument built to exact specifications, on a tight timeline, tight by the standards of a monument meant to last forever, which is to say, within the natural lifetime of the pharaoh who commissioned it, using materials that had to be sourced from locations spread across hundreds of miles of river valley and desert. The challenge was not how to cut a stone. The challenge was how to cut the right stone, shape it to the right dimensions, move it to the right place, and set it in position with the right precision 2 million times in roughly 20 years, without any of the material technologies we now consider essential to large-scale construction. 20 years. Historians estimate the pyramid's construction ran from approximately 2580 to 2560 BCE, though these dates carry uncertainty in either direction. 20 years is 7,305 days. Divide 2.3 million blocks by 7,305, and you get a number that has astonished every engineer and historian who has ever run it. Approximately 315 blocks placed per day. 1 block every 4.5 minutes, every single day, for 2 decades, including presumably the annual flood season, when the site itself may have been partially inaccessible to certain kinds of work, and the inevitable pauses for ceremony, illness, death, and the 1,000 other interruptions that attend any long human endeavor. This was not a casual undertaking. It was the most sustained, organized, and demanding logistical operation the world had seen up to that point in its history, and it demands to be understood not merely as an architectural wonder, not merely as a tomb, however grand, but as a triumph of systems thinking, of institutional knowledge, of management sophistication, and of the deeply human capacity to look at a problem so vast it seems impossible and break it, methodically, into pieces small enough to solve. Khufu's pyramid was the moonshot of the Bronze Age, not in the sense that it was a gamble by the time Khufu commissioned it. The Egyptians had been building pyramids for generations and had accumulated the knowledge base to be reasonably confident in their methods. It was a moonshot in the sense that it required a civilization to organize everything it knew, everything it had, and every person it could coordinate, toward a single, impossibly ambitious goal. and then to actually achieve it. What did it cost? The Egyptians kept no accounting. We have yet found that totals the full human and material expense of the Great Pyramid. We can only estimate tens of thousands of workers at peak activity, millions of man-hours of labor, vast quantities of copper smelted into tools and then resmelted as those tools wore away, forests of timber consumed for sledges, rollers, boat hulls, and scaffolding, an unbroken supply chain of food, bread, beer, beef, fish, feeding workers who burned enormous quantities of calories under the Egyptian sun, a river navigation network purpose-built and then maintained for 2 decades. All of this, sustained, all of it, coordinated. What we do know, from the archaeology, from the papyrus records that survive, from the careful study of the plateau itself, is that the Egyptians were extraordinarily good at all of it. The pyramid that stands today, even stripped of its original white casing stones, even worn by 4,500 years of weather and human depredation, is sufficient proof that the systems behind its construction worked. They worked at a scale and to a standard of quality that the modern world has rarely matched and never exceeded in the purely human sense. Without engines, without electricity, without any of the amplifying technologies that we have come to regard as prerequisites for civilization's largest ambitions, there is something both humbling and exhilarating in sitting with that fact. Humbling, because it dismantles a certain comfortable arrogance about modernity, the assumption that the people of the ancient world were primitive, limited, cognitively smaller than ourselves. They were not. The evidence of the pyramid is the evidence of minds operating at the full range of human intellectual capacity, planning, problem-solving, managing complexity, teaching and learning across generations, and executing, day after day, a plan whose scale dwarfs most things we build today. Exhilarating, because it expands our sense of what human beings have always been capable of when they choose to organize themselves around a shared purpose, large enough to demand their best. The sun is fully up over the plateau now. The morning air, which was almost cool an hour ago, is already warming toward the savage heat of the Egyptian midday. Somewhere below the escarpment, the first gangs of workers are already moving. The sounds of copper on stone are beginning, a rhythmic, ringing percussion that will not stop for 20 years. Somewhere in the administrative building near the harbor, a scribe named Mira, or someone very much like him, is uncapping his ink jar and preparing to log the day's work. How many blocks moved? From where? By whom? To where? The mountain is not yet a mountain. It is an idea, a plan, a set of surveyed lines in the desert floor, and the massed intention of tens of thousands of people organized into a machine for turning intention into stone. It will work. Segment 2, counting the cost. Before a single copper chisel rang against limestone at the Giza Plateau, before a single wooden sledge was dragged across the desert floor, before the first papyrus logistics document was drafted in the administrative offices near the harbor, someone had to reckon with the number. The number was brutal in its simplicity and terrifying in its implications, and once you understood it clearly, everything else about the Great Pyramid, every decision about workforce organization, quarry placement, ramp design, food supply, boat construction, and tool manufacturing cascades directly from it. The number was this: 2.3 million blocks of stone, to be placed in roughly 7,300 working days. That works out, as we noted, to approximately 315 blocks per day. But that average, when you start pulling it apart, reveals layers of complexity that the average figure conceals. The pyramid was not a uniform structure. Its construction was a process that changed in character, in difficulty, and in required precision at every stage. The early courses, the lowest layers of the pyramid, were composed of the largest and heaviest blocks. These were the core foundation courses, often weighing 2.5 to 3 tons per block, and they had to be not merely placed, but placed correctly, because every block above them for the next 481 feet of height would depend on their accuracy. A misalignment at the base was not a minor error. It was a cascading catastrophe that would express itself, amplified, in every course that followed. Getting the base right was the precondition for getting anything else right at all. The base courses also contained the largest volume of stone. The pyramid's geometry meant that the lower portion of the structure, the first 100 feet or so of height, contained the overwhelming majority of its total stone volume. As the pyramid rose, each successive course was smaller in both area and, gradually, in the size of the individual blocks. This meant that the rate of block placement wasn't constant. The project's early years were dominated by the movement of enormous quantities of heavy stone, while the later years involved fewer and lighter blocks but required them to be lifted to heights that created entirely different logistical challenges. Imagine managing this transition. You build your entire workforce, your tool supply, your food supply, your quarrying operation, and your transport infrastructure to handle the maximum demand of the early construction phase. Thousands of workers moving hundreds of blocks a day, requiring prodigious quantities of copper chisels, wooden sledges, papyrus rope, and grain. Then, as the pyramid rises, the nature of the work begins to shift. You need fewer bulk haulers and more precision workers. You need less horizontal transport and more vertical lift capability. The ramps that served perfectly well for the lower courses may be entirely inadequate for the upper sections. The workforce that was right-sized for peak block movement is now either underemployed or needs to be redeployed to different tasks. This kind of dynamic resource management, across a project lasting 2 decades and employing tens of thousands of people, required administrative systems of considerable sophistication. We know those systems existed. The evidence is everywhere in the archaeology of the Giza Plateau. The workers' village, excavated by Zahi Hawass and Mark Lenner south of the pyramid complex, was not a rough encampment. It was a planned settlement, with distinct neighborhoods for different classes of workers, centralized food production facilities scaled to the population they served, and organizational infrastructure that speaks to careful, deliberate management. The bakeries found at the site were not small household operations. They were industrial facilities capable of producing thousands of loaves per day. The brewery adjacent to the bakery suggests that the traditional Egyptian workers' ration of bread and beer was being produced at scale, systematically, as a managed supply operation rather than an improvised one. Beer, in ancient Egypt, was not merely a recreational beverage, it was a nutritional cornerstone. Egyptian beer of this period was thick, nutrient-dense, made from partially fermented grain, and contained significant caloric value. For workers performing heavy physical labor under intense heat, burning perhaps 4,000 to 5,000 calories a day, the combination of bread and beer provided a substantial portion of the energy their bodies demanded. The logistics of feeding the pyramid workforce were, in their own right, a supply chain challenge comparable in complexity to the stone movement operation itself. Grain had to be grown along the Nile, harvested, transported to Giza, stored without spoiling, and then processed into bread and beer at a rate that matched the workforce's daily consumption. A workforce of 20,000 people eating 2 to 3 pounds of bread per day requires roughly 30 tons of processed grain daily, every day, for 20 years. The cattle bones found in the workers' village suggest that beef was also a regular part of the diet, not a luxury but a practical necessity for workers whose bodies needed sustained protein to recover from the physical demands of moving stone. Sheep and goat bones are present too, indicating a diversified protein supply. Fish from the Nile supplemented the diet. The workers at Giza were, by the standards of their era, remarkably well fed. This was not generosity for its own sake. It was operational necessity. A malnourished worker cannot pull a 2.5-ton block. A sick worker cannot cut stone. A dead worker cannot be replaced quickly. The investment in worker nutrition was a direct investment in construction throughput. Beyond food, the project demanded materials in quantities that strained the productive capacity of the Egyptian state. Copper was perhaps the most critically constrained resource. The pyramid's construction required copper chisels, copper saws, copper adzes, copper drills, and copper blades in enormous quantities, constantly. Copper is a soft metal. A copper chisel cutting through hard limestone dulls rapidly. After a few hours of heavy use, a chisel that was sharp and effective in the morning has become blunt and requires resharpening or recasting. The pyramid's quarrying operation burned through copper tools at a rate that necessitated not merely a supply of the raw metal but an entire industrial infrastructure of smelting, casting, and sharpening workshops operating continuously on the plateau. The copper itself came primarily from the mines of the Sinai Peninsula, ancient mines at Wadi Magara and Serebit el-Qadim that the Egyptians had been working for generations. These were not casual extraction operations. They were organized state enterprises, staffed by teams of miners who worked in organized shifts, under official oversight, producing copper, or that was then smelted and shaped into ingots for transport to Giza. The supply chain from Sinai copper mine to Pyramid Quarry face ran across the Sinai Desert, across the Suez region, and down the delta to Giza, a journey of several weeks by the transport methods available. Any disruption to this supply chain, a Sinai raid, a transport failure, a smelting accident, would ripple forward to slow or stop the quarrying operation at Giza within days. Wood was another critical and constrained material. Egypt is not, and was not in antiquity, a heavily forested country. The Nile Valley provided acacia and sycamore, both useful for construction, but neither in the quantities that the pyramid project demanded. Cedar wood of sufficient quality for large sledges, boat hulls, and structural elements had to be imported from Lebanon, a trade relationship the Egyptians maintained through the port of Byblos on the Lebanese coast. The logistics of importing Lebanese cedar, transporting it by sea to the Egyptian delta, moving it upriver to Giza, and then processing it into the dozens of specific forms the project required, added another layer of complexity and another potential point of failure to an already enormously complex supply chain. The papyrus rope industry is worth pausing on. Rope was the fundamental binding and pulling technology of the pyramid project. Every sledge moved by human muscle power required rope. Every block hoisted up a ramp required rope. Every boat's rigging was rope. The anchoring systems, the pulling teams, the hundreds of specific applications that required something strong, flexible, and reliably manufactured, all of it required papyrus rope in quantities that boggle the mind. Papyrus grew abundantly along the Nile, but harvesting it, processing it, spinning it into fibers, and then weaving those fibers into rope of sufficient strength for heavy construction work was a labor-intensive process requiring skilled workers. Rope making was an industry in its own right, and the pyramid project's appetite for rope was essentially unlimited. Now layer on top of all of this the human management challenge. The pyramid's workforce was not a static body of permanently employed laborers. Evidence suggests it was organized around a rotational corvée labor system, a form of labor tax in which farmers and craftsmen from throughout Egypt were conscripted to serve for defined periods of time, typically during the Nile's flood season when agricultural work was impossible anyway. This system had the advantage of distributing the burden of pyramid labor across the entire population rather than concentrating it in a permanent underclass. It had the disadvantage from a management perspective of creating a workforce that was constantly turning over, with experienced workers completing their service and returning home while new workers arrived unfamiliar with the site, the procedures, and the specific skills their roles required. Managing this constant churn required extensive training systems, clearly defined roles that could be learned quickly, experienced permanent workers who could supervise and train the rotating conscripts, and administrative systems capable of tracking who was present, what they were doing, and what they had produced. The named work gangs documented in the archaeological record, each with its own foreman, its own identity, and apparently its own sense of competitive pride, were partly an administrative convenience and partly a management strategy. Giving workers a group identity and a name created cohesion and accountability within the constant flux of the rotational system. It gave people something to belong to, and belonging creates the kind of sustained effort that an impersonal labor draft cannot. Counting the cost of the Great Pyramid is ultimately an exercise in recognizing that the stones themselves were only the most visible element of a far larger enterprise. The stones required tools, and the tools required copper, and the copper required mining and smelting and transport. The stones required workers, and the workers required food, and the food required agriculture and grain storage and baking and brewing at industrial scale. The workers required housing and medical care and management. The management required scribes and papyrus and ink and administrative systems, sophisticated enough to track the movement of millions of objects and tens of thousands of people across 2 decades and hundreds of miles. The pyramid is often described as a feat of construction. It was equally a feat of accounting in the broadest sense of that word. Someone had to count the blocks and the chisels and the bread loaves and the rope lengths and the boat cargoes and the grain sacks. Someone had to add those numbers up, project them forward, identify the gaps, and fill them before the gaps became crises. Someone had to see the whole operation as a system, understand how each part depended on every other part, and manage the entire interconnected web of supply and demand, skill and need, across the full span of the project. That someone, or more likely, those many someones, working within an institutional framework that preserved and transmitted knowledge from one generation to the next, did their job with a thoroughness and effectiveness that is written permanently into the plateau at Giza. The pyramid stands because the accounting was right. Segment 3, Quarrying, where it all began. Everything begins with stone, not with architecture, not with pharaonic vision, not with the engineering calculations of master builders working through the implications of a 481-foot monument, but with stone, specifically with the act of separating stone from the earth that holds it, in the right shape, to the right dimensions, without shattering it into uselessness, at the rate of hundreds of blocks per day for 20 years. Quarrying was not the glamorous part of the Great Pyramid's story. There are no dramatic paintings of quarrying in the tombs of officials, no heroic reliefs showing copper-wielding craftsmen attacking cliff faces. Quarrying was the dirty, relentless, physically punishing foundation of everything else, the process without which no pyramid could exist, and which had to be performed correctly, consistently, and at enormous scale, or the entire enterprise would grind to a halt. To understand the quarrying operation, you first have to understand the geology. The Giza Plateau and the surrounding Nile Valley sit atop vast deposits of nummulitic limestone, a sedimentary rock formed from the compressed shells of ancient marine organisms, laid down in horizontal beds over millions of years when the region was covered by a shallow sea. This limestone is the construction material of the Great Pyramid's core. It is not a single uniform substance. It varies significantly in quality from bed to bed and location to location. Some beds are dense, hard, and fine-grained, suitable for the pyramid's outer casing, where precision surfaces were required. Other beds are softer, more porous, and less regular, still perfectly acceptable for the pyramid's interior bulk, where what mattered was mass and structural support rather than surface quality. The quarrymen of ancient Egypt were geologists in the practical sense. They could read a rock face, identify the quality of different beds, and make rapid judgments about where to cut and where to leave the stone in place. The primary quarrying tool was the copper chisel. These were not the delicate instruments of a jeweler or a sculptor. They were working tools, made in standardized sizes, small chisels for precise work, larger ones for bulk removal, and they were used with a flat wooden mallet to drive the cutting edge into stone. The technique was essentially percussive. You struck the chisel in a line, drove it a fraction of an inch deeper with each blow, and worked your way along the intended cut. With limestone of moderate hardness, an experienced quarryman could cut several inches per hour. Harder stone required more time and more tool replacement. The copper edge dulled quickly against abrasive limestone, and a quarryman who tried to work with a blunted tool was wasting his effort. The dull chisel skidded and slipped, rather than cutting cleanly, and the energy of each mallet blow was lost to friction rather than converted into cutting progress. This is why the tool sharpening and recasting operation at Giza was so integral to the quarrying system. Dull chisels were not simply discarded. They were collected, bundled, and taken to the workshops where smiths heated them in charcoal furnaces, reshaped the dulled edges with hammer and anvil, quenched the hot copper in water to harden it, and returned the recharged tool to the quarry face. The cycle of use, dull, collect, resharpen, return was continuous throughout the working day, and the workshops that supported it were as critical to the quarrying operation as the quarrymen themselves. For the initial rough separation of a block from the bedrock, Egyptian quarrymen also exploited a technique of brilliant simplicity that required no metal at all: wooden wedges and water. The process began with the quarryman reading the stone face to identify natural lines of weakness, existing cracks, bedding planes, the boundaries between geological layers. These natural features were the quarryman's allies because they defined the path of least resistance along which the stone wanted to break. Working along these lines, the quarryman cut a series of slots, rectangular notches spaced evenly along the intended break line, using copper chisels. The slots were cut to a precise depth and angle, designed to receive a wooden wedge of a specific size. Once the slots were cut, dry wooden wedges were driven in firmly with a mallet. Then water was poured over the wedges. Wood, saturated with water, expands, not enormously, but with great force and with a consistency that is eminently controllable by a quarryman who knows his stone. As the wood swelled into the confined space of the slot, it exerted outward pressure on the walls of the cut, pressure that was amplified, focused, and directed along the intended break line. The stone, which had resisted the direct blows of the chisel that first cut the slots, was now being pushed apart from the inside along a line of carefully engineered weakness. Given time, sometimes hours, sometimes overnight, the stone cracked along the intended line with a sound like a thunderclap, and a new block was free from the living rock. This technique was not unique to Egypt. Variants of it have been discovered in quarrying traditions from India to Scandinavia, discovered independently by peoples who faced the same problem and converged on the same elegant solution. But the Egyptians were using it with systematic efficiency at enormous scale, and the evidence of their work is visible today in quarry faces throughout the Nile Valley. Rows of evenly spaced wedge slots, frozen in stone where the work stopped 4,500 years ago, preserving in perfect detail the method used to tear mountains apart one block at a time. After initial separation, the rough block still needed to be shaped, brought from its raw, irregular form to the approximate dimensions specified by the architects for its intended position in the pyramid. This dressing process was carried out by a different class of worker, the stone finishers, who used copper chisels, flint tools, and abrasive rubbing stones to smooth faces, square corners, and bring the block within acceptable tolerances. The degree of finish required varied by the block's intended function. Core blocks buried deep in the pyramid's interior needed only to be roughly rectangular, precise enough to stack stably, but not held to fine tolerances. Casing blocks destined for the pyramid's visible exterior surface were held to extraordinarily tight standards, their faces dressed flat to within millimeters, their joints prepared to fit against adjacent blocks with a precision that, when achieved, left seams nearly invisible to the naked eye. The granite blocks used in the pyramid's interior chambers, the King's Chamber, the Grand Gallery, the various stress-relieving chambers above, presented a qualitatively different quarrying challenge. Granite is an igneous rock, formed from cooled magma, and its crystalline structure is far harder and more resistant than limestone. Copper chisels that cut limestone readily simply skated off granite without making meaningful progress. The Egyptians solved this problem through abrasion rather than percussion. They used harder materials, dolerite, a basaltic rock almost as hard as granite itself, as hammerstones, pounding them against the granite face to crush and chip away the surface grain by grain rather than cutting it cleanly. They also used abrasive slurries, mixtures of hard sand and water, in combination with copper tubular drills to bore holes and saws to cut along marked lines. The process was laborious beyond modern imagination. Cutting a granite block to specification might take weeks of sustained abrasive work, where the equivalent limestone block could be roughed out in hours. All of this required not merely skill but organizational discipline applied at the quarry level. A quarrying operation producing hundreds of blocks per day was not a collection of independent craftsmen doing as they pleased. It was a choreographed production system in which different specialists performed defined roles in a sequence. Geologists read the rock face and marked cut lines. Wedge slot cutters worked along the marked lines. Waterboys maintained the swelling wedges. Breakers prepared for the crack and controlled the block's final separation. Dressers shaped the rough block to specification. Quality inspectors measured and approved the finished product before it was moved. Miss any step, or perform any step carelessly, and the entire block was at risk. A crack in the wrong place, a face that was out of square, a dimension that was off by an inch too many, and hours or days of labor became waste. The rate of production was managed through the gang system. Each named gang had a defined work area, a defined daily quota, and a foreman responsible for meeting it. Competition between gangs documented in the graffiti and textual records of the period was apparently real and apparently encouraged by the management. A gang that exceeded its quota earned recognition. A gang that fell short was accountable for the shortfall. This combination of defined responsibility, measurable output, and competitive pride created the incentive structure that kept the quarrying operation moving at the pace the pyramid's timeline demanded. At peak activity, the main quarry at Giza, the enormous scar in the plateau south of the pyramid, was producing hundreds of blocks daily. The sounds of the operation must have been extraordinary. The rhythmic ring of copper on stone, multiplied by hundreds of simultaneous workers across a quarry face hundreds of yards long. The crack and rumble of large blocks separating from the bedrock. The shouts of foremen coordinating teams. The dull thud of wooden mallets driving wedges. The scraping of dressed blocks being levered onto sledges for transport to the pyramid. Dust hung in the air continuously. The ground was littered with stone chips and copper filings. It was loud, it was hot, it was physically brutal, and it ran, without meaningful interruption, for the better part of 2 decades. The quarry was also a site of ongoing engineering problem-solving. As the excavation deepened and widened, the logistics of getting blocks out of the quarry pit and onto the transport path became more complex. Ramps of packed rubble and mud brick were constructed within the quarry itself, allowing sledges to be pulled from lower excavation levels up to the surface. These internal quarry ramps were continually modified as the extraction front moved, requiring their own maintenance workforce and their own materials. The quarry was not just a mine, it was an active construction project in its own right, constantly reconfiguring itself to maintain access to the stone and the extraction rate the project demanded. What is perhaps most remarkable about the quarrying operation, viewed as a whole, is that it worked, not occasionally, not approximately, but at the sustained industrial scale that the pyramid's eventual reality proves. The evidence is the pyramid itself, 2.3 million blocks, each one quarried, shaped, and delivered to its position. The quarry operation was the heartbeat of the entire project, the pulse without which nothing else could move. And for 20 years, it did not miss a beat. Segment 4. The Giza Quarry, right next door. In the management of any large construction project, one of the most consequential decisions made is rarely the most glamorous. Where do you get your material? And how far does it have to travel? These are not questions that make for dramatic storytelling. They don't appear in the heroic accounts, the poetic inscriptions, or the temple reliefs, but they determine, more than almost any other factor, whether a project is feasible, how long it will take, and what it will cost in human effort and material resources. The architects and planners of the Great Pyramid understood this with a clarity that, once you see it laid out in the geography of the Giza Plateau, seems almost startlingly obvious, and yet represents a level of logistical sophistication that not every culture in comparable circumstances has managed to achieve. They built the pyramid where the stone already was. This sounds simple. It is, in its way, almost comically simple. But the implications are profound, and the decision to exploit the Giza Plateau's existing limestone deposits as the primary source for the pyramids core blocks saved an amount of human labor that is genuinely difficult to calculate, but almost certainly runs into the millions of man-hours. The vast majority of the pyramid's 2.3 million blocks, estimates range from 80 to 90% of the total, representing somewhere between 1.8 and 2 million individual stones, came not from distant quarries requiring long transport journeys, but from a massive extraction site located directly to the south and southwest of the pyramid's base. On the same plateau, sometimes within a few hundred meters of where the blocks would ultimately be placed. Today, tourists visiting Giza walk past this quarry without recognizing it. It is not signed or interpreted the way the pyramids themselves are. It appears as a large, irregular depression in the plateau, an area where the landscape dips and opens into what looks, to the untrained eye, like natural geological variation. But it is not natural. It is a man-made void, the negative space left by the removal of millions of tons of limestone over the course of the pyramid's construction. Walk its perimeter, and you are walking around the ghost of the pyramid. The stone that isn't there anymore, because it is now over your shoulder, stacked into one of the most recognizable shapes in human history. The strategic advantage of this arrangement was not lost on the architects who planned it. Consider the alternative. If the core blocks had needed to be transported from the Tura quarries on the Nile's eastern bank, which were the source of the higher quality limestone used for the pyramid's casing, the entire operation would have been an order of magnitude more complex and demanding. The Tura limestone required a river crossing. Blocks had to be loaded onto boats, ferried across the Nile, unloaded at a dock, and then moved overland to the pyramid site. This was manageable for the casing stones, which were required in relatively smaller quantities, and whose quality justified the extra effort and cost. But subjecting 2 million heavy core blocks to that same journey would have been logistically catastrophic, demanding a fleet of boats so large it would have strained Egypt's entire shipbuilding and maritime capacity, and a river crossing operation so massive and continuous that any disruption to it would have halted construction almost immediately. By using the Plateau quarry for core blocks, the architects eliminated the river crossing from the majority of the transport equation. A block quarried at the Plateau quarry needed to travel, in most cases, only a few hundred meters to a few kilometers to reach its final position. At the base courses where the largest blocks were placed and the transport demand was at its maximum, the quarry face was sometimes almost directly adjacent to the construction perimeter. Workers cutting blocks at the near edge of the quarry in the early construction phases could have placed those blocks the same day they were extracted, a logistical arrangement so efficient it seems almost too good to be true. The transport of core blocks from the Plateau quarry to the pyramid followed a well-established procedure that the Egyptians had refined through earlier pyramid projects. Blocks were levered off the quarry floor onto wooden sledges using wooden poles and stone or copper fulcrums. Teams of workers the size of the team scaled to the weight of the block pulled the sledge across the limestone surface using papyrus rope, with a worker stationed at the front of the sledge pouring water or a slurry of wet clay onto the surface ahead. The lubricating effect of the wet surface was significant. Studies of Egyptian sledge transport have estimated that a properly lubricated limestone surface reduces the friction coefficient by roughly half compared to dry stone, effectively doubling the load a given pulling team could move. The routes from quarry to pyramid were not random. They were engineered pathways, prepared surfaces of compacted rubble, tamped earth, and in some sections what appears to have been a form of mortar or plaster, designed to provide a consistent sliding surface for the sledge runners. These hauling roads show up clearly in the archaeology of the plateau: worn channels in the bedrock, deposits of construction material in characteristic linear patterns, areas where the surface was deliberately leveled or filled to provide a continuous grade. They were, in essence, purpose-built logistics infrastructure, the ancient equivalent of a haul road in a modern quarry operation, maintained and repaired as needed to keep the blocks moving. The distance from quarry to pyramid base varied across the construction period. In the early phases, when the pyramid's footprint was being established and the lower courses laid, the extraction front was close to the construction zone and haul distances were short. As the quarry was worked outward and downward, as workers ate further into the plateau's limestone reserves, the average haul distance increased. This was a manageable increase, never approaching the distances involved in the Tura or Aswan supply chains, but it required that the hauling road network be periodically extended and that the logistics of moving blocks from deeper in the quarry to the pyramid face be continuously recalculated. The timing of quarrying activity at the Plateau quarry was also carefully managed in relation to the construction schedule. The early construction phases, when the largest volumes of core block were needed most rapidly, correspond to what would have been the period of maximum quarrying intensity at the Plateau site. As the pyramid rose and the demand for large core blocks diminished, the upper courses used smaller blocks, and the interior chambers and passages required precision-cut blocks rather than bulk limestone. The quarrying operation at the Plateau site could be correspondingly reduced and the workforce redeployed to other tasks: finishing work, casing stone installation, internal passage construction, or the finishing of the plateau's auxiliary structures. There is also a feature of the Plateau quarry that speaks to the depth of planning that went into the pyramid project. The quarry was designed, implicitly, to produce the specific kind of material the project needed at each phase. The limestone of the plateau varies in quality by depth and by location within the deposit. The architects and quarry managers understood this variation well enough to direct extraction selectively, pulling higher quality stone for positions in the pyramid where quality mattered more, using lesser quality stone for the deep interior where it would never be seen and where structural mass rather than surface quality was the relevant property. This selective extraction required geological knowledge, planning, and coordination between the quarry operation and the construction management. Another layer of systemic sophistication wrapped inside what might appear, from a distance, to be a simple decision about where to dig. The decision to locate the pyramid on the Giza plateau was likely made for multiple reasons: religious and symbolic significance, the plateau's solid bedrock foundation, its proximity to the Nile, its visibility from the valley below. But one of the most practically significant reasons, whether the decision-makers articulated it in these terms or not, was that the plateau was sitting on top of an enormous, accessible, adequate quality limestone deposit that could serve as the primary material source for the largest structure in the ancient world. The pyramid site and the quarry site were, in the most literal sense, the same place. This is what sophisticated logistics looks like in practice. Not the dramatic solution, not the heroic technology, not the secret that explains the inexplicable, but the quiet, methodical recognition of a geographical advantage and the organizational discipline to exploit it fully. The greatest construction project of the ancient world was built, in substantial part, from its own backyard. The people who planned that had understood something fundamental about the relationship between material supply and construction efficiency that would not be articulated as formal theory for another 4,000 years, but which they applied, correctly and effectively, at a scale that still defines human achievement. Khufu built a harbor at Giza. This is no longer an inference or a hypothesis. It is a documented fact, with the documentation written by someone who used the harbor as part of his regular working routine. The harbor received deliveries of the fine Tora limestone casing stones, the high-quality material that formed the pyramid's outer surface, the smooth white face that would have gleamed in the Egyptian sun when the pyramid was new. It also almost certainly received granite deliveries from Aswan, and possibly other materials transported by river. The harbor was, in effect, Giza's receiving dock, the point where the riverborne supply chain handed off to the overland transport operation that completed the final leg of the journey from water to construction site. The physical evidence for the harbor and its associated canal system has been partially confirmed by ground survey and, more recently, by remote sensing studies of the Giza Plateau and surrounding area. Traces of ancient waterways are visible in satellite imagery and in the geological record of the area. Linear depressions, sediment deposits characteristic of standing water, and the remains of what appear to have been key structures along the hypothesized canal routes. The picture that emerges is of a water network specifically engineered to support the pyramid project. Canals dug or deepened to channel Nile floodwater close to the plateau. Quays and loading facilities built to standard specifications for the boats and blocks they handled, and a logistics infrastructure that converted the Nile from a distant highway into one that effectively extended to the pyramid's doorstep. The engineering of this hydraulic infrastructure is worth dwelling on, because it is easy to underestimate both its complexity and its strategic importance. The Giza Plateau rises above the Nile floodplain. The natural Nile bank was some distance from the pyramid site, and the direct approach between the river and the plateau involved navigating a change in elevation as well as a change in terrain. The Egyptians bridged this gap with canals that followed natural topographic contours where possible, exploiting low-lying areas and seasonal watercourses to minimize the excavation required. During the annual flood season, when the Nile's level rose by as much as 20 to 25 feet, the reach of navigable water expanded dramatically. Canals that were too shallow for loaded boats at low water became fully navigable channels at flood peak. The construction schedule was synchronized with this seasonal reality. The period of maximum stone delivery by water coincided with the flood season, when the hydraulic infrastructure was at its maximum effectiveness. This synchronization between natural hydrology and construction logistics is one of the most elegant features of the entire pyramid operation. The Egyptians did not fight the Nile's seasonal behavior. They designed their supply chain around it, treating the annual flood not as a disruption to be managed, but as a resource to be exploited. The quarrying operations at distant sites ramped up in the months before the flood, stockpiling stone at loading quays along the river. When the flood came and raised the water level, the fully loaded boats could be moved with maximum efficiency, their cargoes delivered to Giza through canals that the low water season would have made impassable. When the flood receded, the boats were repositioned, the quarries were restocked, and the cycle began again. Mira's diary gives us a window into this system in operation. His team was not an anomaly. They were one of presumably many similar teams, each responsible for their segment of the supply chain, each moving their cargo of stone through the hydraulic network on a schedule coordinated by administrators whose names we don't know but whose organizational intelligence is written into the system that Mira describes. The scale of the boat operation required to support the pyramid's construction has been estimated by various researchers, working from the quantities of casing stone and granite needed, the likely cargo capacity of boats of the period, and the duration of the navigable season. The numbers suggest that hundreds of boat trips were required annually during the peak construction period, a maritime logistics operation comparable in scale to a significant commercial port of the ancient world. The boats themselves were sophisticated vessels, not primitive rafts or dugouts. Egyptian boat building of the Old Kingdom period was a mature technology, producing wooden vessels capable of carrying dozens of tons of stone cargo. The famous Khufu ship, a full-size cedar vessel dismantled in a pit adjacent to the Great Pyramid in 1954, reassembled, and now displayed in a dedicated museum on the plateau, is not a transport barge but a royal ceremonial vessel, built to different specifications than the working boats of the supply chain. But it demonstrates the level of boat-building craft available in Khufu's era. Skilled construction in cedarwood, using mortise and lash joinery rather than nails, producing a vessel of considerable size and structural sophistication. The working boats that carried pyramid stone were built to different proportions, wider, flatter, more heavily reinforced at the hull to carry the distributed weight of stone blocks without structural failure. Loading these boats with massive blocks of limestone or granite was itself a logistical operation, requiring purpose-built infrastructure, loading ramps or key structures at the quarry end, where blocks could be slid or rolled from storage area to boat deck, and unloading facilities at the Giza harbor, where blocks were offloaded and transferred to sledges for the overland leg of the journey. The transition points, quarry to boat, boat to canal, canal to quay, quay to sledge, were the critical junctions in the supply chain, the places where delays and failures most easily accumulated, and where the quality of the infrastructure and the competence of the managing officials made the largest difference to overall throughput. Mira's diary records his team stopping at various points along their route to interact with officials, inspectors, administrators, supply managers, whose roles were clearly defined and whose presence along the route was systematic rather than coincidental. This network of administrative oversight along the supply chain ensured quality control. Stones were inspected and approved at the quarry before loading, re-inspected on delivery, and also provided the information flow that allowed the central administration to monitor progress, identify bottlenecks, and redirect resources as needed. The pyramid was not just a construction project, it was an information management challenge, requiring a constant upward flow of operational data from hundreds of simultaneous activities to a small group of planners who had to integrate it all into a coherent picture and make decisions that kept the entire system moving. The harbor at Giza and the canal network that connected it to the Nile represent perhaps the least celebrated and most essential element of the Great Pyramid's construction logistics. The ramps get the attention, the stone cutting gets the admiration, and the sheer scale of the workforce gets the statistics-driven awe. But none of it works without the water. The Nile was not merely the backdrop against which the pyramid was built. It was an active participant, a logistics resource, a transportation network, and a seasonal partner whose rhythms the builders had studied carefully and incorporated into their plans. Khufu didn't just build a pyramid, he built the infrastructure to build a pyramid, and the harbor was the keystone of that infrastructure, the point where the river's power was harnessed, focused, and delivered directly to the stone mountain rising on the plateau above. Segment 7. The Nile as Highway. There is a temptation, when studying the Great Pyramid, to focus entirely on the plateau, on the quarry, the ramps, the workers' village, the construction site itself. The plateau is where the drama is most visible, where the stone is, where the monument stands. But this focus creates a distortion, because the Great Pyramid was not built on an island. It was built at the end of a supply chain that stretched hundreds of miles in multiple directions, and the connective tissue of that supply chain, the medium through which the overwhelming majority of its long-distance freight moved, was the Nile River. Understanding the pyramid means understanding the Nile not as scenery but as infrastructure, the most important linear logistics asset in the ancient world, a natural highway that the Egyptians had been studying, using, and adapting to their purposes for centuries before the first stone at Giza was cut. The Nile is, in physical terms, an anomaly. It is the longest river in the world, running approximately 4,130 miles from its headwaters in Central Africa to its delta on the Mediterranean coast. But unlike most great rivers, which drain broad, well-watered catchment basins and maintain relatively consistent flow throughout the year, the Nile in Egypt runs through one of the driest environments on Earth, a narrow ribbon of fertility in the middle of the Sahara, sustained entirely by rainfall and snowmelt, occurring thousands of miles to the south in the Ethiopian highlands and equatorial Africa. For most of the year, the Egyptian Nile runs at a moderate level between its banks, navigable but not dramatically different from its dry season state. Then, predictably, reliably, every year between roughly June and October, the river transforms. The floodwaters arrive from the south, swelling the Nile too many times its dry season volume, spreading across the floodplain in an inundation that the ancient Egyptians called Arkit, the season of flooding, and which they regarded not with dread but with gratitude, because the waters carried the rich silt that fertilized their fields and the elevation that extended the reach of their river transport far beyond the low-water channel. For the pyramid builders, the annual inundation was not an obstacle to be endured. It was a scheduled logistical event to be exploited with maximum efficiency. The planning calendar of the pyramid project was built around the Nile's seasonal cycle in the same way that a modern shipping company builds its schedule around port capacity and vessel availability. Each phase of the year brought different logistical opportunities and constraints, and the Egyptians had learned, through generations of agricultural management, river trade, and earlier construction projects, exactly how to read those opportunities and align their operations with them. During the dry season, from roughly November through May, the Nile ran at its lowest levels. The main river channel was navigable for boats of moderate draft, but the floodplain on either side was dry land, and the network of canals that connected the river to inland sites and quarrying operations was at its shallowest and least navigable. This was the season for overland work, for the quarrying operations at the Giza Plateau itself, for the finishing and dressing of blocks that had been delivered during the flood season, for the actual placement of stone on the pyramid's rising form, for the maintenance and improvement of ramps and hauling roads, and for the 1,000 construction tasks that didn't require moving heavy material long distances by water. The dry season was, in a sense, the season of construction in the direct sense, the time when workers built, fitted, and raised. As the dry season ended and the first signs of the approaching flood appeared, a slight reddening of the water from Ethiopian sediment, a barely perceptible rise in the river level that experienced river watchers could detect weeks before the full inundation arrived. The logistics operation shifted into a different mode. Quarrying teams at the Tura limestone sites on the Nile's eastern bank began working at maximum intensity, cutting and dressing casing blocks to specification and staging them at the riverside quays. At Aswan, 500 miles to the south, the granite quarrying teams accelerated their own operations, leveraging the rising river to move increasingly heavy loads to the loading docks with less effort. Boat crews inspected and repaired their vessels, checked rigging and oars, and prepared for a season of intensive freight operations. When the flood arrived in earnest, typically in late July or August, the hydraulic geography of the Giza region transformed almost overnight. The low-lying areas between the river and the plateau, which had been dry land for most of the year, filled with water. The canals that Khufu's engineers had dug and deepened became navigable channels capable of passing fully laden stone barges. The harbor at Giza, which in the dry season sat at the edge of the inundated zone, was now a working port directly accessible by riverboat. The effective distance between the Tura quarry and the pyramid construction site, measured not in physical miles but in the effort required to move a stone from one to the other, shrank dramatically, because the river had come to them. The boats used for pyramid stone transport during the flood season were working vessels of considerable size and structural robustness. They needed to be a cargo of fine Tura limestone casing blocks, each one weighing 2 to 4 tons. Dozens of them loaded per trip represented a total freight weight that could easily reach 100 tons or more per boat. The whole structure had to distribute this weight without failure. The bottom planking had to be thick enough to resist the abrasion of loading and unloading operations, and the overall proportions of the vessel had to be optimized for the specific conditions of Nile navigation. Relatively shallow draft for the canal sections, sufficient beam for stability under heavy load, and a hull form that could be propelled efficiently with oar and sail in the variable wind conditions of the Nile Valley. The Nile's prevailing winds in Egypt blow consistently from north to south, from the Mediterranean toward the interior. This is a meteorological fact of extraordinary logistical convenience for a civilization oriented along a north-south river axis. Boats, traveling south, upstream, against the current, could simply raise a sail and let the wind push them. Boats traveling north, downstream, with the current, could lower the sail and use the current's energy to carry them without significant rowing effort. The result was a natural two-way logistics system in which the river's physics handled much of the propulsive work in both directions, reducing the crew size and energy expenditure required for a given cargo movement. The Egyptians didn't invent this fortunate arrangement, but they had understood it thoroughly for centuries and built their entire economy of river transport around it. Stone barges traveling from Aswan to Giza, a journey of roughly 500 miles, were making a downstream journey, carried northward by the current. Their crews needed to steer, to manage the cargo's stability, and to navigate the various features of the river. But the fundamental propulsive work was done by gravity acting on the river water. A fully loaded granite barge leaving Aswan in late July could expect to arrive at Giza in roughly 2 weeks, depending on the strength of the current and the navigational conditions encountered en route. Empty barges returning to Aswan for the next load could raise their sails and use the north wind to push them back upstream, typically in a somewhat longer journey of 3 to 4 weeks, but still not requiring significant human energy expenditure. The management of the boat fleet was a logistics operation in its own right. Boats were assets of significant value. A large stone barge represented weeks of skilled labor in its construction, expensive imported cedar in its hull, and specialized equipment in its rigging. They required maintenance, repair, and periodic reconstruction as the hard service of stone transport wore on their hulls and fittings. Boat crews were specialists whose skills in navigation, cargo management, and vessel operation were not interchangeable with the quarrying or construction workforce. The harbor at Giza needed to be managed as an active port facility, with designated berths for incoming and outgoing vessels, a system for offloading blocks without damaging the dock structure or the stone, storage areas for blocks awaiting overland transport, and administrative staff capable of tracking inbound shipments against the construction schedule's requirements. The coordination between the river operation and the construction site was mediated by exactly the kind of administrative oversight that Mira's diary documents. An official like Mira was not just moving stones, he was generating information, creating a paper trail of deliveries that allowed the central administration at Giza to know, in real time by the standards of the ancient world, what material was in transit, what had been delivered, and what remained to be sourced. This information was the foundation of the supply planning operation, the data that allowed the master architects and their administrative staff to project forward, identify upcoming shortfalls before they became crises, and direct resources to address them. Consider the complexity of that planning challenge. At any given moment during the flood season, dozens of boats might be simultaneously in transit between various quarry sites in Giza. Some carried casing limestone from Tura, others carried granite from Aswan, a longer journey requiring more advanced planning and a longer lead time between ordering and delivery. Still others might carry wood, copper, food supplies, or other materials needed at the construction site. Each of these flows had its own schedule, its own capacity constraints, and its own vulnerability to disruption. A boat grounded on a sandbar, a storm that scattered a convoy, a quarry problem that delayed loading. Any of these events upstream in the supply chain would propagate downstream to the construction site, reducing the availability of material and slowing the rate of block placement. Managing these disruptions required not just administrative competence but a kind of anticipatory thinking, the ability to identify likely failure modes in advance and build contingency capacity into the system. The Egyptians appear to have done this through buffer stocks, staging areas at both quarry and construction ends of the supply chain where blocks could be accumulated during periods of high production and drawn down during disruptions. Mira's diary mentions blocks being inspected and staged at the Tura quarry before loading, a practice consistent with building an upstream buffer. Similar staging areas at the Giza harbor end would have provided a cushion between river delivery and construction demand, smoothing out the inevitable irregularities in delivery schedules. The Nile also provided something more subtle, but equally important, a shared temporal reference for the entire logistics system. Because the river's seasonal cycle was the same everywhere along its Egyptian length, the flood rose and fell on roughly the same schedule. From Aswan to the delta, everyone in the system was working from the same seasonal clock. Quarry managers in Aswan, boat captains on the river, harbor officials at Giza, and construction managers on the plateau all calibrated their plans to the same annual rhythm. This shared temporal framework simplified coordination enormously. It meant that the question of when to prepare for the flood, when to maximize loading, when to transition from river transport to overland operations, was not something that needed to be negotiated or communicated anew each year. It was embedded in the institutional knowledge of everyone involved, part of the practiced routines of a civilization that had been working with the Nile's rhythms for generations. The Nile, in this sense, was not just a highway. It was a clock, a calendar, and a planning framework, the temporal structure around which the entire pyramid logistics system was organized. The river told you when to quarry more aggressively, when to launch the boats, when to shift your workforce from transport to construction, and when to begin preparing for the next year's cycle. Following the river's calendar didn't require sophisticated communication or complex coordination. It required the deep, practical knowledge of a civilization that had been paying attention to the same river for centuries, learning what it offered, and building systems sophisticated enough to take full advantage. 4,500 years after the last casing stone was set at Giza, the Nile still runs north from Aswan, past the Plateau, still floods each year in its reduced modern form, still reflects the light of the same indifferent sun. The harbor has silted over, the canals are dry, and the boats that once carried granite and limestone to the pyramid's base have long since rotted to nothing. But the river remains, and in its patient, seasonal flow, there is still an echo of the extraordinary logistics operation that once rode its waters, the operation that carried a mountain's worth of stone to a desert plateau and stacked it, block by block, into a monument that has outlasted every civilization that has looked upon it in wonder. Segment 8, Ramps, the Great Debate. Of all the questions that clustered around the Great Pyramid's construction, and there are many, each one capable of generating years of scholarly argument, none has proven more durable, more contested, or more genuinely unresolved than the question of the ramps. How did the ancient Egyptians get multi-ton blocks of stone up the rising face of the pyramid, from the ground to their final positions at heights reaching nearly 500 feet? What mechanism bridged the gap between the ground and the sky? The answer, almost certainly, involved some form of inclined surface, a ramp of sufficient slope and structural integrity to allow a loaded sledge to be hauled upward by human muscle power. Beyond that point of near consensus, everything becomes debate, and the debate has been running, with increasing archaeological sophistication and decreasing certainty of resolution, for the better part of 2 centuries. The debate matters because the ramp is not a detail. It is, in certain respects, the central mechanical problem of the entire construction enterprise. Moving a 2.5-ton block horizontally on a lubricated sledge across prepared ground is a demanding but tractable problem. We have the physics, the evidence, and the comparative examples to understand it reasonably well. Moving that same block vertically, lifting it from the level of the plateau to a position 100, 200, or 300 feet above, is a fundamentally different challenge, one that multiplies the required effort by the height of the lift and introduces engineering challenges of slope, structural support, and surface management that have no equivalent in the horizontal transport operation. The ramp was the solution. Understanding what kind of ramp is understanding something essential about how the pyramid was actually built. Begin with the physics, because the physics constrain every theory before archaeology or architecture gets a word in. A ramp allows a heavy load to be raised by converting horizontal travel distance into vertical height gain. You trade effort over a longer path for reduced effort at each point along that path. The steeper the ramp, the shorter the path, but the greater the effort required at any given moment. The shallower the ramp, the longer the path, but the more manageable the effort. For a loaded sledge being pulled by teams of human workers, there is a practical upper limit to the gradient they can manage before the combination of load weight, friction, and slope angle exceeds what coordinated muscle power can deliver. Experimental archaeology and biomechanical modeling both suggest that the maximum practical gradient for loaded sledge transport is somewhere between about 1 inch minus 10 and 1 inch minus 12. That is, the ramp rises 1 unit of height for every 10 to 12 units of horizontal length. Apply this constraint to the pyramid's geometry and the implications are immediate and sobering. The pyramid's full height is approximately 481 feet. To build a ramp reaching that height at a gradient of unintent requires a ramp approximately 4,800 feet, nearly a mile in length. At a gradient of unin 12, the ramp would need to be nearly 5,800 feet long. A ramp of this length, wide enough to allow loaded sledges to pass, and sturdy enough to support multi-ton loads, would itself be a construction project of enormous scale, requiring vast quantities of mud brick, rubble, compacted earth, and gypsum mortar, all needing to be organized, transported, and placed in a structure that had to remain stable and functional throughout the pyramid's entire construction period. This is the fundamental problem with what has traditionally been called the straight ramp theory, the hypothesis that a single massive ramp extended from the plateau surface directly to the rising face of the pyramid, growing longer as the pyramid grew taller. The theory has the advantage of simplicity. A straight ramp is easy to understand, easy to build incrementally, and easy to use. It has the disadvantage of an almost fatal arithmetic. Egyptologists who have worked through the numbers in detail have calculated that a straight ramp of the necessary length and cross-section to serve the pyramid's full height would have required more material than the pyramid itself. The tail, in this scenario, becomes larger than the dog. And then there is the question of what happened to all that ramp material when the pyramid was finished. Dismantling a structure of that scale would have been a significant project in its own right, and the plateau shows no obvious deposit of the hundreds of millions of cubic feet of mud brick and rubble that such a ramp would have required. Modifications of the straight ramp theory attempt to address this by positing that the full-height straight ramp was never needed. that a shorter, steeper ramp served the lower courses, where the blocks were heaviest and most numerous, and that a different system was used for the upper portion of the pyramid, where blocks were smaller and the required quantities were much lower. This hybrid approach has genuine appeal. It acknowledges that the lower pyramid, where perhaps 80% of the total stone volume is concentrated, is the critical logistics challenge, and that solving the lower pyramid's transport problem with a manageable straight ramp while using a different lighter system for the upper pyramid avoids the worst of the arithmetic difficulties. But it requires two separate systems and two separate engineering solutions, and it leaves the question of what the upper pyramid system was entirely open. The spiral ramp theory proposes an alternative geometry, rather than extending straight out from one face. The ramp winds around the outside of the pyramid like a continuous helical shelf, hugging the pyramid's rising form and growing with it as successive courses are added. The spiral ramp has a significant theoretical advantage over the straight ramp. It keeps the ramp's total length proportional to the pyramid's perimeter at each level, rather than requiring it to extend outward from a single face, which dramatically reduces the total material required. The structural demands are also more manageable. The ramp is supported partly by the pyramid itself at each level, rather than needing to be entirely but the spiral ramp has its own critical weakness, and it is one that Egyptologists have identified with considerable force. It would have made accurate surveying of the pyramid's corners essentially impossible during construction. The pyramid's extraordinary geometric precision, its corners aligned to the cardinal directions, to within 1/10 of a degree, its sides level to within 2 centimeters across their full length, required continuous, unobstructed access to the corner points, and the ability to sight lines from corner to corner, and from base to apex throughout the construction process. A ramp winding around the outside of the pyramid would have buried the corners under rubble for the entire construction period, eliminating the reference points that the surveyors needed to maintain precision. A pyramid built with a spiral ramp covering its corners would almost certainly show the accumulated errors of that surveying handicap, and the Great Pyramid manifestly does not. Its precision argues strongly against any system that blocked corner access during construction. It was into this apparently irresolvable impasse, the straight ramp too large, the external spiral too imprecise, that French architect and pyramid specialist Jean-Pierre Houdin introduced, in 2007, a theory that has attracted both significant support and significant skepticism, but has undeniably changed the character of the debate. Houdin's proposal, developed over years of computer modeling and structural analysis, posits that the Egyptians used a two-stage system, a straight external ramp of manageable length for the lower third of the pyramid, where the block volumes were greatest and the height to be gained was within the straight ramp's feasible range, followed by a system of internal spiral tunnels for the upper two-thirds of the structure. In Houdin's model, as the external ramp reached its maximum practical length and the pyramid's height exceeded what the straight ramp could efficiently serve, workers began using a different route, an internal ramp cut into the pyramid's own body, spiraling upward through the massive stone in a continuous helical tunnel. At the pyramid's corners, where the internal spiral would need to change direction, open notches cut into the outer face of the pyramid at each level allowed blocks to be pivoted around the corner and continue their upward journey. Once a course was complete and the notch was no longer needed, it was filled in with casing blocks that matched the surrounding surface. The internal spiral, entirely enclosed within the pyramid's mass, would have left the exterior corners unobstructed and the surveying reference points continuously accessible throughout construction. The elegance of Houdin's theory is compelling. It explains the pyramid's precision, avoids the material excess of the straight ramp, and provides a rational engineering solution to the upper pyramid lifting problem that is consistent with the Egyptians' known capabilities and materials. The theory received a significant, though not conclusive, boost from a 2011 analysis using a technique called microgravimetry, measuring tiny variations in the gravitational field at the pyramid's surface to detect density anomalies that might indicate internal voids. The results showed an anomalous zone at the pyramid's upper levels consistent with the spiral tunnel geometry Houdin predicted. This is not proof. Microgravimetry at these scales is a subtle technique, and the interpretation of the anomaly is contested. But it is the kind of physical evidence that keeps a theory alive. Further support has come from the ongoing program of scanning and non-invasive survey work at Giza, most notably the Scan Pyramids project, a multinational scientific collaboration that has been using muon radiography, infrared thermography, and other non-invasive techniques to probe the pyramid's interior since 2015. Muon radiography, a technique that uses the penetrating power of cosmic ray muons to image the density distribution inside large structures, has revealed several previously unknown voids within the Great Pyramid's mass. The most significant of these, announced in 2017, is a large void above the Grand Gallery, at least 30 meters long, whose precise shape, orientation, and structural purpose remain under investigation. Whether any of these voids correspond to internal ramp tunnels, stress-relieving chambers, or features related to the pyramid's construction logistics is an open question, but the existence of unknown large-scale features within the pyramid's body is itself a reminder that the structure still holds secrets. What most Egyptologists who work closely with the evidence today will tell you is that the ramp question probably does not have a single, clean answer, that the pyramid's construction almost certainly employed different systems at different stages, adapted to the changing geometry and logistics of the project as it rose toward completion. A straight or broadly angled ramp for the heavy early courses, transitioning to some form of spiral or stepped system for the upper reaches, possibly with elements of both internal and external routing, depending on the specific requirements of each phase. This kind of adaptive, pragmatic approach is consistent with what we know about how the Egyptians approached engineering challenges generally. They were not theorists committed to a single elegant solution. They were practitioners who used what worked and changed what didn't. The ramp debate will likely continue for decades, perhaps centuries, because the definitive evidence is sealed inside a 4,500-year-old mountain of stone that the world's governments are not about to allow anyone to excavate destructively. The pyramid keeps its secrets, not through mystical concealment, but through sheer mass. The answers are in there, and getting to them without destroying the thing we're trying to understand is a puzzle that neither archaeology nor physics has yet solved. In the meantime, the debate itself is illuminating, because every theory proposed forces its proponents to reckon seriously with the same constraints: physics, logistics, material volumes, workforce capability, geometric precision that the original builders had to solve. In trying to reverse engineer their solution, we come closer to understanding the quality of mind that produced it. Segment 9. The workforce organized like an army. For more than 1,000 years after the Great Pyramid was built, visitors to Giza who were told it had been constructed by human hands simply did not believe it. The Greeks, who visited the Plateau in significant numbers during the classical period, concluded that the pyramids must have been built by slaves, vast armies of the brutalized and the coerced, driven to their deaths under the whips of Egyptian taskmasters. Herodotus, who visited Egypt around 450 BCE, reported this interpretation as fact, transmitting it to the Western world with the authority of direct observation. The slave narrative was not merely convenient, it was, to ancient and later observers alike, the only explanation that seemed to fit the scale of the undertaking. Only unlimited, disposable human suffering could have produced something so enormous. Only fear could have organized labor on this scale. The archaeology says otherwise. The archaeology says something far more interesting, more human, and in certain respects more remarkable than the slave narrative, because it requires us to understand the Great Pyramid, not as the product of terror, but as the product of an extraordinarily sophisticated system of labor organization, worker welfare, and institutional management that produced, in the people who built the pyramid, something that no slave can be compelled to provide: genuine investment in the quality of the work. The evidence begins with the workers' village. In the late 1980s and through the 1990s, Egyptian archaeologist Zahi Hawass, working in collaboration with American archaeologist Mark Lennox, excavated an extensive settlement located to the south of the Giza pyramid complex, on the plateau itself. What they found was not the improvised encampment of pressed laborers, sleeping in the open and eating whatever scraps their overseers provided. It was a planned, permanent settlement of considerable scale and sophistication, a city within a city, designed from the ground up to support the pyramid workforce at the highest standard of maintenance that the ancient Egyptian state could provide. The settlement's food production infrastructure alone speaks volumes about the scale and intentionality of the operation. The bakeries excavated at the site were not domestic kitchens or small communal operations. They were purpose-built industrial facilities, with rows of conical bread molds of standardized size, large hearth ovens arranged for maximum throughput, and evidence of grain processing at a scale calibrated to feed thousands of people daily. Experimental archaeology conducted at the site estimated that the bakeries, operating at full capacity, could have produced thousands of loaves per day, enough to provide the daily bread ration for a workforce of 10,000 or more workers. The number of bread molds found, the size of the ovens, and the spatial organization of the bakery complex all point to centralized, managed food production that was designed and operated as a supply function rather than improvised as a necessity. Adjacent to the bakeries, the excavators found evidence of brewing operations, large vats, organic residues consistent with fermented grain, and the kind of spatial organization that characterizes industrial-scale beer production. Egyptian beer of this period was not the thin, fizzy beverage we associate with the word today. It was a thick, nutrient-dense, partially fermented grain drink with significant caloric value, closer in its nutritional profile to a liquid meal than to a recreational beverage. For workers expending 4,000 to 6,000 calories per day in heavy physical labor under the Egyptian sun, the combination of bread and beer provided a substantial fraction of their energetic and nutritional requirements. The brewing operation at the workers' village was not a perk or a privilege, it was a component of the nutritional management system that kept the workforce physically capable of performing the work. The protein supply was even more revealing. The animal bones found in the workers' village included cattle, sheep, goat, and pig in quantities and age profiles that strongly suggest these animals were being raised and slaughtered specifically to feed the workforce rather than representing the incidental consumption of a subsistence community. The cattle bones showed that adult animals, representing a significant capital investment in feed and maintenance, were being slaughtered regularly, indicating that beef was a routine rather than occasional component of the diet. Isotopic analysis of the bones and teeth of workers recovered from the nearby cemetery has confirmed that these were individuals who ate well, who consumed protein and calories at levels consistent with a diet actively managed to support sustained heavy labor. The cemetery itself is one of the most important sources of information about the pyramid workforce. Located near the workers' village, it contains the burials of both the skilled permanent workers and the seasonal laborers who staffed the project's peak construction phases. The burials are not the mass graves of expendable slaves, they are individual interments, with grave goods, food offerings, and in many cases simple but genuine funerary care. The skeletons show the characteristic bone deformations associated with heavy physical labor over many years, enlarged muscle attachment points, arthritis of the joints most stressed by quarrying and hauling work, spinal compression injuries consistent with carrying heavy loads. These were the bodies of people who worked extraordinarily hard for most of their adult lives. But the skeletons also show something else, evidence of medical care. Bones with healed fractures, breaks that were set and splintered and allowed to heal correctly, rather than left to fuse at wrong angles, appear with striking frequency in the cemetery. Evidence of amputations, including at least one case of a below-knee amputation from which the individual survived long enough for bone healing to occur, demonstrates that the pyramid's medical establishment was performing complex procedures and that patients were receiving post-operative care sufficient to allow recovery. The survival rate from such procedures in antiquity, without antiseptic technique or anesthesia beyond what plants could provide, was not high. That some survived suggests not just surgical skill but a care infrastructure, a system for keeping injured workers alive and recovering, that contradicts any image of a workforce treated as fully disposable. The organizational structure of the workforce is documented in detail that no other ancient construction project comes close to matching. Workers were organized into named gangs, permanent groups with defined membership, their own foremen, their own identities, and apparently their own competitive pride. The names of these gangs, painted in red ochre on the stones they placed, have been recovered from various locations in and around the pyramid complex. Names like Friends of Khufu, Drunkards of Menkaure, and the Gang, Green appear alongside the marks of individual foremen, and occasionally the names of the workers themselves. These names were not administrative conveniences imposed from above. They were identities that the workers chose and maintained, markers of belonging that expressed the kind of group pride that emerges when people care about the quality of their shared work. Above the gang level, the organizational hierarchy was elaborate and carefully maintained. Gang foremen reported to site supervisors, who oversaw specific sections of the construction. Site supervisors reported to senior officials responsible for major functional areas: quarrying, transport, placement, supply. Those senior officials reported to the vizier, and ultimately to the pharaoh himself. At every level, scribes recorded the activities, outputs, and resource consumption of the tier below, creating an administrative information flow that gave the senior leadership an ongoing picture of the project's status across all its dimensions. This was not a hierarchy of terror. It was a hierarchy of accountability, a system in which everyone knew what they were responsible for, what they were expected to produce, and how their performance would be measured. The rotational labor system that brought the bulk of the workforce to Giza is documented in both textual and physical evidence. Farmers and craftsmen from throughout Egypt were required to serve periodic stints on the pyramid project, typically during the flood season, when agricultural work was impossible and their labor was otherwise idle. They came from the delta, from Upper Egypt, from the mining regions of the eastern desert, drawn from every corner of the kingdom by a labor tax system that was administered with the same bureaucratic thoroughness that characterized every other aspect of Old Kingdom Egyptian governance. Each laborer's service was recorded: their home region, their assigned gang, their duration of service. When their term ended, they returned home with something that no slave could take home: the status of having served the pharaoh, the physical evidence of having contributed to the horizon monument that would be visible from their fields for the rest of their lives. The permanent core workforce, the skilled quarrymen, stonecutters, surveyors, architects, scribes, and specialized craftsmen who maintained continuity across the project's full duration, were a different category. These were career pyramid builders, men who spent their working lives on the plateau and whose accumulated skills were the institutional knowledge base that the rotating seasonal labor depended on. Training new workers each season required this permanent core to serve as instructors, supervisors, and quality controllers, transmitting not just specific techniques, but the broader operational knowledge of how the pyramid system worked and why each element of it mattered. The permanent workforce was the pyramid project's memory, and its maintenance was a deliberate management strategy rather than an accident of continuity. What emerges from all of this evidence is a portrait of the pyramid workforce that defies both the romantic and the cynical interpretations that have dominated popular understanding. It was not a slave army driven by whips. The archaeology is definitive on this point. But neither was it a volunteer enterprise powered purely by religious devotion and civic pride, as some more idealistic accounts have suggested. It was a managed system, disciplined, demanding, and organized with a sophistication that reflects both the Egyptian state's administrative capabilities and its pragmatic understanding that a workforce treated as human beings would outperform one treated as machines. The pyramid builders were compensated in the currency of the ancient world: food, beer, medical care, housing, status, and the spiritual benefit of participating in the construction of a divine monument. They were managed with a combination of accountability and identity that created genuine organizational commitment. And they were organized, from the smallest gang to the highest administrative level, with a clarity of structure and a consistency of record-keeping that produced the throughput and the quality the project required. The pyramid is often discussed as a feat of engineering. It was equally a feat of human management, of the ancient art of getting large numbers of people to work together, effectively, toward a shared goal over a sustained period of time. The people who managed the workforce knew something that organizational theorists would not articulate formally for another 4,000 years: that the quality of the work reflects the quality of the conditions in which it is done, and that the investment in worker welfare is not charity but operational strategy. Segment 10. Copper, the unsung hero. Every great construction project has a material that makes it possible, a substance so fundamental to the operation that without it the entire enterprise grinds to a halt, and yet which, precisely because it is everywhere and always present, receives little of the attention lavished on the more visible elements of the achievement. For the Great Pyramid, that material was stone, obviously, abundantly, undeniably. But for the process that turned raw rock into pyramid, for the operation that extracted, shaped, cut, drilled, dressed, and finished millions of blocks of limestone and granite across 2 decades of continuous industrial effort, the foundational enabling material was something far less celebrated and far less permanent than any of the stone it worked. Copper is a soft metal by the standards of what came after it. The Iron Age would eventually displace the Bronze Age, and iron tools harder, sharper, and more durable than copper would transform metalworking, warfare, and construction across the ancient world. But iron smelting requires temperatures and techniques that were beyond the Egyptian Old Kingdom's capabilities. In 2560 BCE, Copper was the hardest material available in workable quantities for the construction of cutting tools, and the Egyptians had been working with it long enough to understand both its capabilities and its limitations with considerable precision. They knew what copper could do, and they designed their quarrying and stone-cutting operations around exactly what was possible with the tools copper allowed. The copper chisel was the fundamental cutting instrument of the pyramid project. Not a single elaborate or specialized device, but a standardized working tool manufactured in large quantities, used until it dulled, resharpened and returned to use, and eventually recycled into new chisels when the metal was too worn to hold an edge. Archaeological evidence from Old Kingdom sites documents copper chisels in a range of standardized sizes: narrow chisels for detail work and joint preparation, medium chisels for face dressing and groove cutting, larger chisels for bulk stone removal. The standardization itself is significant. It implies a manufacturing operation producing tools to specification, not the ad hoc production of whatever the nearest smith happened to make. Someone was managing the chisel supply chain. The speed with which copper dulled against limestone is the starting point for understanding the scale of the tool supply challenge. Modern experiments using copper replica tools against Egyptian limestone of comparable hardness have documented the dulling rate with reasonable precision. A copper chisel working against moderately hard limestone can expect to maintain its effective cutting edge for somewhere between 15 minutes and an hour of continuous use, depending on the hardness of the specific stone, the angle and force of the blows, and the quality of the copper itself. After that, the edge has rounded and spread sufficiently to be ineffective. The blows still land, but the energy is dispersed over a wider contact area. The stone is no longer being cut cleanly, and the worker is essentially doing no useful work while consuming the same energy and effort as when the chisel was sharp. This is not a trivial constraint. An operation running hundreds of simultaneous quarrying and dressing workers, each consuming 1 to 4 chisels per hour, requires an industrial tool resupply system operating continuously at a very high throughput to keep every worker supplied with functional equipment. The numbers, worked through carefully, are staggering. At 300 simultaneous chisel-using workers, each consuming an average of 2 chisels per hour across a 10-hour working day, the operation requires 6,000 chisel resharpening cycles per day, every day, for 20 years. The workshop infrastructure that supported this demand was not a side operation. It was a central pillar of the construction system, as essential to the pyramid's progress as the quarrying teams and the sledge gangs. The resharpening and recasting operation at Giza worked as a continuous cycle. Dull chisels were collected from workers at intervals throughout the day, perhaps when workers stopped for their bread and beer ration, perhaps when gang foremen making their rounds gathered the dulled tools from each team. The collected chisels were taken to the metalworking workshops that archaeological evidence indicates were located on or near the plateau. There, smiths working at charcoal-fueled furnaces heated the dulled copper to a temperature at which it became workable, not fully molten, but soft enough to be reshaped under hammer and anvil blows. The spread and rounded cutting edge was hammered back to a wedge profile, the blade realigned, and the tool quenched in water to harden the copper through rapid cooling. The resharpened chisel then rejoined the tool pool and was redistributed to workers who needed fresh equipment. This cycle could not run indefinitely without a fresh copper input. Copper is lost in the resharpening process, tiny amounts with each cycle, but cumulative over thousands of cycles and hundreds of thousands of working days. Worn chisels that had been resharpened too many times and were too short or too thin to be useful were re-tied into ingots and recast as new tools. But the process was not perfectly efficient, and there was constant net consumption of copper across the project's lifetime. The supply of fresh copper from the mines of the Sinai Peninsula was not a background consideration. It was a lifeline that had to be maintained without interruption, because the quarrying operation, which fed everything else in the construction system, was directly dependent on a continuous supply of functional cutting tools. The Egyptian copper mining operations in the Sinai were, by the era of the pyramid's construction, well established and extensively developed. The mines at Wadi Megara, which the Egyptians had been working since the First Dynasty, several centuries before, Khufu, and the related sites at Serabit el-Qadim, were not informal surface diggings, but organized industrial operations with galleries cut into the hillside, systematic waste removal, on-site or processing, and the kind of permanent administrative infrastructure that bespeaks long-term, planned exploitation. Royal inscriptions at both sites, carved into the rock face beside the mine galleries, record the names of pharaohs under whose authority the mining expeditions operated, evidence that copper mining was a state enterprise supervised at the highest level of Egyptian government. Mining expeditions to the Sinai were not the casual affairs of a few workers with picks. They were organized military-scale operations, typically dispatched during the cooler winter months when the desert crossing was survivable and the mines themselves were not murderously hot. An expedition might number several hundred people, miners, smelters, guards, to protect against the Bedouin peoples of the Sinai, administrative officials to manage the operation and record its output, support staff to handle food preparation and medical care. The logistics of supplying a Sinai mining expedition were themselves a significant management challenge. Water had to be carried into a waterless desert, food brought from the Nile Valley, tools transported out, and copper or transported back, all across a desert route that offered no natural resources and no margin for navigational error. The ore returned from the Sinai was not pure metal. It was malachite and other copper-bearing minerals, requiring smelting to separate the metal from the gangue material before it could be worked into useful forms. Smelting furnaces at Giza and at transit points along the route between Sinai and the construction site processed the ore into copper ingots, which were then distributed to the Plateau workshops for manufacture into specific tool forms. The smelting operation required charcoal, produced from acacia wood or imported timber, and bellows or blowpipe operators to achieve the temperatures necessary to reduce copper oxide to metal. Managing the charcoal supply added another branch to the logistics tree. Wood had to be sourced, processed, transported, and stored at the smelting sites to keep the furnaces burning. Beyond chisels, copper served the pyramid project in a range of other critical applications. Copper saws, long thin blades used with an abrasive slurry, were essential for cutting granite to the precise dimensions required for the king's chamber lining and the various other precision applications where granite appeared in the pyramid's interior. The saw cut against granite, not by the hardness of the copper blade itself. Copper cannot cut granite directly, but through the abrasive action of the hard sand or powdered stone slurry applied to the saw's path as it moved. The copper blade maintained pressure and guided the cut. The abrasive material did the actual cutting. This process was slow, patient work. Cutting a large granite block face to specification with a copper saw and abrasive slurry might take days, but it was capable of producing the flat, smooth surfaces and precise dimensions that the interior chamber work required. Copper drills operated on a similar principle. A tubular copper drill pressed into a granite surface with a heavy stone weight on top of it, rotated by a wooden handle, with abrasive slurry fed continuously into the drill path. The drill cut not with the copper tube itself, but with the abrasive particles trapped between the tube's edge and the stone surface. The evidence of this technique is preserved in ancient drill cores, cylinders of granite left over from drilling operations, that show the characteristic spiral grooves left by abrasive cutting rather than the cleaner scalloping that would result from a harder cutting edge. These drill cores have been found at Egyptian sites and studied carefully, and their geometry confirms beyond reasonable doubt that the abrasive drilling technique was the standard method for boring into hard stone. The copper adds a broad, curved blade, mounted on a wooden handle at roughly a right angle, was the carpenter's primary shaping tool, used to shape and dress the wooden sledges, rollers, ramps, and structural elements that the construction operation demanded in enormous quantities. As the construction continued for 2 decades and wooden equipment wore out and required replacement, the demand for copper adzes in the carpentry workshops was continuous. The copper draw knife, the copper plane, and various other forms of copper woodworking tool all contributed to the equipment inventory, each one subject to the same cycle of use, dulling, resharpening, and eventual recycling that characterized the chisel supply. What copper represents, in the full context of the pyramid project, is the indispensable interface between human intention and resistant material, the point at which the plans of the architects and the force of the workers' muscles were translated into actual change in the physical state of the stone. Without copper tools in functional condition, the quarrymen could not cut, the dressers could not finish, the carpenters could not build the equipment on which everything else depended. The entire physical production process, from quarry face to finished pyramid, ran through copper. Every supply chain disruption, every quality failure, every shortage of tool stock propagated immediately into reduced production at the point of stone, and reduced stone production meant a slower pyramid, a delayed schedule, and a pharaoh whose horizon monument might not be ready before his horizon arrived. The Egyptians understood this dependency and managed it with the seriousness it deserved, maintaining the Sinai mining operations, supporting the smelting infrastructure, and operating the Plateau workshops as integral components of the construction system rather than support functions. Copper was not glamorous. It wore away invisibly in the course of doing its work, ground to microscopic particles in the gap between tool edge and stone, smelted and recast 100 times before finally being lost to oxidation. But the pyramid is its monument, as surely as it is Khufu's, because without the unceasing, industrial-scale consumption and replenishment of that soft, red metal, the stone would never have moved. Segment 11. Precision, the true marvel. There is a version of the Great Pyramid's story that is entirely about scale, about the millions of blocks and the tens of thousands of workers and the decades of labor and the miles of supply chain. That version of the story is true and important, but it risks obscuring something that is, in a certain sense, even more remarkable than the scale, the precision, because the Great Pyramid is not merely a very large pile of stone. It is a very large pile of stone, assembled to tolerances that challenge the capabilities of modern construction, using instruments and methods that we still do not fully understand, across a surface area of 13 acres and a vertical rise of nearly 500 feet. Without a single error significant enough to compromise the structure's geometric integrity over 4,500 years. The scale tells us that the ancient Egyptians could organize enormous quantities of labor and material. The precision tells us something different and deeper, that they could think. Begin with the base. The Great Pyramid's base is a square, or as close to a perfect square as human measurement has ever achieved at this scale. The four sides, each measuring approximately 756 feet, differ from one another in length by less than 8 inches across a combined perimeter of more than half a mile. The difference between the longest and shortest sides represents a proportional error of approximately 0.1%, a figure that falls within the margin of error of modern construction surveys conducted with electronic total stations. The achievement is not merely that the sides are nearly equal, it is that this equality was achieved without GPS, without electronic measurement, without anything more sophisticated than stretched cords, plumb bobs, and the accumulated knowledge of Egyptian surveying practice. The base is also level, across the full 13-acre extent of the pyramid's foundation. The variation in elevation between the highest and lowest point of the base perimeter is approximately 2.1 centimeters, less than an inch. This extraordinary levelness was almost certainly achieved using water, the most reliable leveling instrument available to any culture before the invention of precision optical instruments. A network of shallow channels cut into the prepared bedrock of the foundation, filled with water to a consistent depth, would have provided a perfectly level reference surface across the entire base area. The surface of still water is gravitationally defined. It seeks the geoid, the shape of the Earth's gravitational equipotential surface, with perfect consistency, regardless of the distance involved. By cutting the foundation surface to match the waterline in these reference channels, Egyptian surveyors could achieve a levelness limited only by the precision with which they could transfer the waterline reference to the stone surface, and the pyramid's base shows that their precision in this transfer was extraordinary. The orientation of the pyramid to the cardinal directions is perhaps the most technically impressive aspect of its geometric precision. The four faces of the Great Pyramid point to within a fraction of a degree of true north, south, east, and west, an alignment so accurate that it has led to speculation over the centuries about lost knowledge or supernatural assistance. The actual explanation requires neither. It requires only the careful, skilled use of astronomical observation. The ancient Egyptians used the circumpolar stars, the stars near the celestial pole that never set below the horizon at Egyptian latitudes, but instead circled the pole continuously as their north reference. By observing the rising and setting of a given circumpolar star against a calibrated instrument, they could determine the precise direction of the celestial pole, which corresponds to true north on the ground. The instrument most likely used for this purpose was the merket, a pair of devices, one a split palm rib used as a sighting tool, the other a plumb line, used together to define a precise vertical and to sight along specific astronomical directions, with two observers using mercats positioned at a known distance apart, sighting on the same circumpolar star at the eastern and western extremes of its nightly arc. The bisector of the angle between those two sightings defines true north with great accuracy. The technique requires patience. You need to observe the star over multiple nights to average out atmospheric effects and measurement errors, but it does not require any technology beyond what the Egyptians certainly had, and it produces results consistent with the pyramid's observed orientation. The interior geometry of the pyramid is continuous with the precision of its exterior, a consistency that reflects a single, unified surveying and quality control system operating throughout the construction, rather than different standards applied to different parts of the structure. The Grand Gallery, the extraordinary corbelled passage that rises at a precise angle of approximately 26 degrees, from the ascending passage to the King's Chamber antechamber, maintains its angle with a consistency that implies continuous survey control throughout its construction. The King's Chamber itself, buried deep in the pyramid's heart, is nearly perfectly rectangular, its walls plumb, its floor level, its ceiling beams flat and horizontal to within tolerances that would be respectable by contemporary construction standards. The exterior casing blocks, the fine Tura limestone facing that originally covered the entire pyramid surface, and of which only a few remain at the base, were dressed and fitted to a standard of surface quality and joint precision that represents the highest achievement of Egyptian stonework. The surviving casing blocks at the base show joint gaps so small that a modern razor blade cannot be inserted between adjacent stones. This is not an accident of good fortune or an exaggeration of ancient sources. It is measurable, documented, and confirmed by every archaeologist and engineer who has examined the stones closely. The joints were prepared by a technique of optical flattening. The mating surfaces of adjacent blocks were dressed by grinding them together with abrasive material until the high spots were removed and the surfaces conformed to each other with full contact across their entire area. The result was a fit that was effectively monolithic blocks that, once placed, behaved as a single continuous surface rather than a jointed assembly. Achieving this quality at the scale of the pyramid's outer casing, thousands of blocks, each one requiring both mating surfaces to be prepared to this standard, required a quality control system operating throughout the casing block production process. Blocks that failed to meet the surface quality standard could not be placed in the visible exterior. They would either be reworked to meet standard or redirected to interior use where joint quality was irrelevant. The inspectors who made these quality decisions were not making aesthetic judgments. They were enforcing a technical specification on which the pyramid's long-term structural integrity and visual appearance depended. A casing block placed with a poor joint would eventually allow water to infiltrate. Desert rain is rare but not absent, and the thermal cycling of the Egyptian climate would work on any weakness in the masonry over the centuries. The stress-relieving system above the King's Chamber is a masterwork of structural engineering that reveals the depth of the pyramid builders' understanding of compressive load management. The King's Chamber roof consists of 9 enormous granite beams, each weighing approximately 25 to 40 tons, spanning the chamber's width of about 17 feet. The total load of pyramid stone above the chamber runs to hundreds of thousands of tons, enough to crush any spanning structure if applied as a simple point load on the roof beams. The Egyptians addressed this problem not by making the roof beams stronger, there is a limit to what even granite beams of this size can span, but by removing the load from them. Above the King's Chamber roof are 5 successive compartments, separated by flat granite slabs, the uppermost of which is topped, not with a flat roof, but with a corbelled apex, 2 inclined granite slabs, meeting at a ridge. This system distributes the overhead load outward to the solid pyramid mass on either side of the chamber, essentially creating a stress-relieving arch that channels the compressive forces away from the chamber roof and into the surrounding stone. There has been no structural failure in the King's Chamber in 4,500 years. The beams show cracking. Several of the granite ceiling slabs have visible fractures, likely the result of the seismic activity that has affected the Giza region over the millennia. But the cracks are held in place by the surrounding structure, which continues to perform its load-distributing function correctly. The chamber has not collapsed. The roof has not failed. The structural solution, devised by engineers who had no formal mechanics, no calculational tools beyond geometry, and no material testing capability beyond empirical experience, has outlasted every comparable structure built in the intervening 4.5 millennia. Understanding how the surveyors maintained this precision across the full duration of the project is perhaps the deepest puzzle of all. A construction project lasting 20 years involves continuous disruption. Workers come and go, ramps are built and modified, equipment is changed, and the physical environment of the work surface is constantly shifting as the pyramid grows. maintaining survey control in this environment, keeping the reference points accessible, checking and correcting the alignment and level of each course before the next is placed on top of it, ensuring that the accumulated errors of 20 years of measurement and placement don't compound into gross deviations from the design, required a continuous program of survey work running parallel to and integrated with the construction work itself. The pyramid's precision is, in the end, the most direct and incontrovertible evidence we have of the quality of mind that built it. Scale can be achieved by throwing enough resources at a problem. Precision cannot. Precision requires understanding of geometry, of measurement, of error control, of the way that small mistakes compound over large distances and long durations if they are not caught and corrected. The Great Pyramid's precision tells us that the people who built it understood these things, not as abstract principles, not as formal theory, but as the deep, practical, hard-won knowledge of professionals who had thought carefully about a difficult problem and developed the tools, the techniques, and the discipline to solve it at a scale that still commands the respect of anyone who measures it carefully. Segment 12. The legacy in the stone. The last casing stone was set. The white limestone surface, dressed to a mirror finish and fitted joint to joint with its neighbors in the seamless continuity that the ancient Egyptians had achieved across every course of the outer facing, caught the morning light and threw it back across the desert plateau in a blaze that would have been visible from the hills east of the Nile, from the fields where the farmers who had rotated through the construction workforce were now tending their wheat, from the boats on the river that had carried stone and grain and copper and wood to the plateau for 2 decades. From a sufficient distance, on a clear day, and most days in the Egyptian desert are clear, the finished pyramid would have appeared to shimmer, a white mountain of light rising from the tawny plateau, geometric and absolute, more permanent looking than anything else on the horizon. Khufu may not have lived to see this moment. The pyramid's construction spanned roughly 20 years, and if he commissioned it early in his reign, he may have died with the capstone still in progress, or only recently placed, or he may have stood on the plateau as an old man, attended by officials and priests, and watched the final casing stones take their positions with the quiet satisfaction of a man who had set himself the most ambitious task in the history of the world and seen it through. We don't know. The historical record of Khufu's personal life is remarkably sparse for a man who left the largest monument in human history. We know his name, we know his family relationships, we have a single small ivory statuette that is the only surviving representation of him, and we have his pyramid. The rest is silence. What the pyramid itself speaks, across the silence of 4,500 years, is worth listening to carefully, not for the mystical significance that generations of romantics and cranks have projected onto it, but for what it actually says about the civilization that built it and the human capacities it demonstrates. What it says, first and most simply, is that a civilization operating entirely without the material technologies we consider essential to large-scale construction, without steel, without engines, without computers, without industrial-scale manufacturing, was nonetheless capable of organizing, supplying, and executing the largest construction project the world had seen or would see for 4,000 years after its completion. The pyramid is evidence against the comfortable assumption that technological sophistication is a prerequisite for organizational sophistication. The ancient Egyptians had one without the other, and what they achieved with organizational sophistication alone should give pause to anyone inclined to measure civilizational achievement primarily in terms of material technology. The organizational sophistication on display in the pyramid project was not narrow or specialized. It ran across every dimension of what we now call supply chain management, project management, workforce management, logistics, and quality control. The people who planned and executed the pyramid project understood how to decompose an enormous goal into manageable subgoals, assign responsibility for each subgoal to defined organizational units, measure performance against those responsibilities, and adjust the system dynamically in response to what the measurements revealed. They understood how to build buffer capacity into supply chains to absorb inevitable disruptions without propagating them to the construction front. They understood how to synchronize multiple parallel activities: quarrying, transport, ramp construction, stone placement, tool supply, food supply, so that each fed the others at the right rate and none became a chronic bottleneck. They understood how to invest in worker welfare as an operational strategy rather than treating it as an ethical luxury. They understood, in short, how to manage a complex system, and the Great Pyramid is the evidence of that understanding. The logistics of the Nile supply chain, the harbor, the canals, the seasonal coordination, the fleet of stone barges, the inspection and staging systems documented in Mira's diary, represent a hydraulic logistics network of a sophistication that would not be matched in the Western world until the canal-building era of the 18th century CE. The Egyptians did not merely use a river that happened to be nearby. They engineered the connection between the river and their construction site, building purpose-specific infrastructure to maximize the river's logistical utility. And they managed that infrastructure with the administrative precision that the project's scale demanded. This was systems thinking applied to geography, a recognition that the physical environment was not a fixed constraint to be accepted, but a resource to be shaped and leveraged. The precision of the pyramid's geometry, the level base, the aligned faces, the fitted joints, the structural engineering of the internal chambers, represents an intellectual achievement of the highest order, one that required not just skill, but a theoretical understanding of measurement, error, and geometric constraint that had no formal mathematical language to express it, but was nonetheless operating at a level of sophistication that produced results indistinguishable from those a modern surveyor would achieve with GPS and electronic total stations. The Egyptians who leveled the base and aligned the faces were not following a recipe handed down from a divine source. They were solving an engineering problem with the tools available to them, and they solved it better than it has been solved at comparable scale before or since. The workforce management system, the workers' village, the food supply, the medical care, the named gangs with their competitive pride, the rotational Quarry system that distributed the burden across the population while maintaining quality through a permanent skilled core, represents a model of labor organization that recognized, 4,500 years before modern management theory formalized it, that human beings work best when they are treated as human beings. The pyramid was not built by fear. It was built by a combination of obligation. The Quarry system was a tax, not a choice, and genuine investment, both on the part of the state that fed and housed and cared for the workers, and on the part of the workers who left their names on the stones they placed and carried those names home when their service was done. The copper supply chain, the boat-building industry, the rope-making operations, the tool workshops. Each of these support systems was itself an organizational achievement of considerable complexity, requiring planning, investment, and management across geographic scales that extended from the Sinai Peninsula in the east to the granite quarries of Aswan in the south, from the cedar forests of Lebanon to the fields and breweries of the Egyptian Nile Valley. The Pyramid Project was not an isolated construction operation. It was a mobilization of the full productive capacity of one of the ancient world's most sophisticated civilizations, directed with focus and discipline toward a single monument. What is perhaps most remarkable, in the long view, is that the Egyptians had done this before and knew they would need to do it again. The Great Pyramid was not built in ignorance of its predecessors. Sneferu, Khufu's father, had built 3 significant pyramids, the Medum Pyramid, the Bent Pyramid, and the Red Pyramid, each one incorporating lessons learned from the previous, each one a step in the development of the technical and organizational systems that the Great Pyramid would employ at maximum scale. Hemunu and his contemporaries did not invent pyramid building. They inherited it, studied it, understood its failures as well as its successes, and applied that accumulated institutional knowledge to the greatest project the tradition had yet attempted. The Great Pyramid was the culmination of a learning curve, the expression of multi-generational institutional knowledge refined by experience and applied with the full resources of a confident, organized, capable state. In the centuries and millennia that followed, the pyramid outlasted the civilization that built it, the dynasty that ordered it, the administrative systems that managed its construction, and the very religious framework that gave it meaning. The Old Kingdom collapsed around 2160 BCE, roughly 4 centuries after the pyramid was completed, and Egypt passed through periods of fragmentation, foreign conquest, religious transformation, and cultural revolution that would have been unrecognizable to the workers who set the last casing stone. The pyramid stood through all of it, stripped gradually of its white limestone casing by later builders quarrying convenient stone, its capstone lost at some unknown point, its interior plundered of whatever portable wealth it once contained. But the geometric form, the engineered mass, the structural logic of 2.3 million blocks assembled with precision and care, these endured. Napoleon Bonaparte, standing before the Great Pyramid in August 1798, during his Egyptian campaign, reportedly performed a quick calculation and told his officers that the stone in the 3 pyramids of Giza could build a wall 10 feet high and 1 foot thick around the entire perimeter of France. The calculation is roughly correct. The numbers work out approximately. It is the kind of quantitative observation that appeals to a military man accustomed to thinking in terms of logistics and resources, but it misses what is actually remarkable about the pyramid, which is not the quantity of the stone, but the quality of the thinking that moved it. The wall around France would be a barrier, an obstacle, a boundary, a thing defined entirely by its extent and its function. The Great Pyramid is something else entirely, a monument to the proposition that human beings, organizing themselves with sufficient intelligence and discipline and care, can accomplish what appears impossible. Not through supernatural assistance, not through lost technologies, not through alien intervention. These explanations are all, in their different ways, insults to the people who actually did the work. Through planning, through organization, through the patient, systematic application of available knowledge and available tools to a problem that was enormous in scale, but tractable in its components. One block at a time, one chisel stroke at a time, one boat voyage at a time, one carefully measured and leveled course at a time. The sun sets over the Giza Plateau the same way it has for 4,500 years, sliding below the western horizon in a blaze of orange and red, casting long shadows eastward across the stone. The pyramid catches the last light on its western face, holds it for a moment in the way that rough ancient stone holds warmth from the day's heat, and then releases it to the desert dark. In the morning, the light will return, and the pyramid will be there to receive it, as it has been every morning since the last casing block was placed, and the last worker walked down from the plateau and went home to wherever home was. It is still there. That is the final thing. The logistics of the Great Pyramid teaches us the most durable lesson written in 2.3 million blocks of carefully moved stone, that the things we build with sufficient intelligence, sufficient care, and sufficient organizational commitment outlast almost everything else. The pharaoh is dust. The workers are dust. The ropes and the sledges and the copper chisels are dust. The harbor has silted over. The canals are dry, and the administrative papyri that tracked every block and every boat cargo have mostly crumbled to nothing. But the pyramid stands, precisely where Hemunu placed it, precisely as level and precisely as aligned as the day it was completed, a permanent argument against the idea that what is difficult is impossible, and a permanent monument to the human capacity, when properly organized, properly motivated, and properly fed, to move mountains. Here is the conclusion with the closing greeting. The Great Pyramid of Giza does not ask for your belief. It does not require your wonder, though wonder is the natural response of anyone who stands at its base and cranes their neck upward toward the place where its ancient edges still converge against the Egyptian sky. It does not need your theories or your reverence or your speculation about the forces that produced it. It simply stands as it has stood through the reign of 100 civilizations, through the rise and fall of empires that considered themselves eternal, through the slow grinding of centuries that have reduced most of what the ancient world built to rubble and legend and footnote. It stands on the same plateau where Khufu's surveyors stretched their cords and read their stars. It stands on the bedrock from which its own core blocks were cut, over the ghost of the quarry that fed it, above the silted traces of the harbor that supplied it. It is, in the most literal sense, its own site, monument, and evidence, simultaneously, the achievement and the record of the achievement fused into a single, indestructible form. What this series has tried to do, across 12 segments and the full sweep of the pyramid's construction story, is restore to the Great Pyramid the human dimension that centuries of mystification have obscured. The pyramid is not a mystery. It is a solution, the solution that a particular group of extraordinarily capable human beings developed over generations of accumulated learning and institutional refinement to the problem of building the largest structure their civilization had ever attempted. The solution involved copper chisels and papyrus rope and wooden sledges and water poured onto limestone to reduce friction. It involved a harbor engineered to bring the Nile to the plateau's edge and a fleet of wooden boats that rode the seasonal flood with their cargoes of stone. It involved bakeries producing thousands of loaves a day, and breweries producing the beer that sustained workers burning through calories at rates that would humble a modern athlete. It involved named work gangs with competitive pride, and middle managers like Mira, keeping meticulous diaries of every boat trip and every stone delivery. It involved surveyors reading the circumpolar stars to find true north, and scribes in administrative offices turning operational data into decisions that kept 2 million blocks moving toward their final positions on a schedule that never, across 20 years and the full depth of human contingency, fell irreparably behind. Every element of that solution was human. Every piece of rope was twisted by human hands, from papyrus harvested by human hands from the Nile's edge. Every copper chisel was cast by a human smith in a human workshop, from ore mined by human workers in the Sinai desert. Every block that moved across the plateau moved because human muscles pulled on human-made rope, attached to a human-built sledge, sliding across a surface, wetted by a human carrying a human-made pot of water. The organizational intelligence that coordinated all of this, that held the supply chains together, and the workforce organized and the survey control maintained, and the quality standards enforced across 2 decades of continuous industrial effort, was human intelligence, the full cognitive capacity of people, no different from us in their fundamental nature. Different only in what they knew and what they had, and what they were asked to do with it. This is, ultimately, what makes the Great Pyramid so deeply worth understanding. Not its scale, though the scale is staggering, not its precision, though the precision is humbling, but what it proves about the range of human capability when human beings organize themselves around a sufficiently ambitious shared purpose with sufficient intelligence and care. The pyramid is evidence that civilization's deepest technologies are not material but organizational, not the tools we make but the systems we build for deploying those tools at scale, for maintaining quality across distance and time, for managing the inevitable friction of large human endeavors without letting that friction accumulate into failure. These technologies were already mature 4,500 years ago, demonstrated at a scale that most modern organizations would not attempt. The stone is their monument, the precision is their signature, the endurance is their final argument. When the last worker walked down from the Giza Plateau at the project's completion, they left behind something that has outlasted everything else they ever touched. Their bread is gone, their beer is gone, their rope and their sledges and their copper chisels are gone. Their names, with a few exceptions, scratched in red paint on hidden stones, are gone. But the thing they built, the thing they moved all those stones to create, 1 block every 4.5 minutes for 20 years, remains, as precise and as present as the morning it was finished, catching the same light, casting the same shadows, standing on the same plateau above the same river that carried their stone and fed their children and marked the seasons of their working lives. They are gone, but what they made with their hands and their minds and their extraordinarily capable civilization is not gone, and will not be gone for a very long time yet. The horizon of Khufu endures. That was always the point. Good night, traveler, wherever you are in the world as these words find you. Whether the sun has just set over your city or is still climbing toward noon. Whether you are winding down from a long day or stealing a quiet moment from a busy one, carry something of this story with you into whatever comes next. You have just spent time in the company of people who lived 4,500 years ago and who moved mountains with their bare hands, their brilliant minds, and their refusal to accept that the impossible was anything more than the not yet solved. That is not a bad thing to take with you into the night. Rest well. The pyramid will still be there in the morning.